Good morning, students. Welcome back to this algorithm class. This is Professor Michael. We are discussing about dynamic programming. In the last class, we solved one example problem based on dynamic programming problem solving strategy, that was string editing. That is converting one string from to another string with some editing operations, and each editing operation has a cost involved in it. The aim is to convert one string into another with minimum editing cost. That was the problem that we have discussed in the last class. In this class, we are going to discuss about yet another problem called traveling salesman problem. This problem involves graph. You know what is a graph is? A graph is a abstract data structure made up of vertices and edges, and edges are lines connecting two vertices. uh, okay, a graph might have n number of vertices, and a set of all these vertices are put into a set called V, and a collection of all the edges are put into a set called E. So generally, to represent a graph, we say that G is equal. We say it as G of V comma E, where V is the set of vertices, E is the set of edges. Now, coming to this traveling salesman problem. um, Before this, I want you to know what is a cycle in a graph, what is a tour in a graph. A cycle in a graph is starting from one vertex and visiting few vertices and coming back to that same vertices, same vertex. That is called a cycle. A cycle need not go through all the vertices of a graph. Okay. But coming to what is a tour is basically a cycle. It starts from one vertex and visit all the vertices of the graph and come back to the starting vertex. Underline the word all the vertices. So a tour is basically a cycle starting from one vertex, visiting all the vertices and coming back to the original vertex. That is called a tour. Now, a graph might have several tours. A graph might have several tours. And the cost of a tour is the sum of edges involved in the tour. Sum of edges. The sum of the weight of the edges involved in the tour. So every tour has a cost involved to it, and the traveling salesman problem is to find the minimum cost tour. Minimum cost tour. So with that understanding, let us describe this problem. Okay, this is the problem definition. You are given a graph G with set of vertices V and set of edges E, and Cij is the weight of the edge between vertex I and vertex J. Cij is the cost of the edge between the vertex I and J. Let us assume that there are n vertices in the graph, and I told you what is a cycle is. Tour of G is a cycle having all the vertices of G. So the cost of the tour is the sum of the weight of the edges in the tour. Sum of the weight of the edges in the tour. Now the traveling salesman problem is to find a tour of minimum length, that is minimum cost. Okay, that is our problem is. How are we going to solve this problem using this dynamic programming problem solving strategy? Okay. Okay, for our convenience sake, let us take we start from vertex 1, from vertex 1. So we are going to visit all the vertices and come back to the vertex 1. such that the cost of the tour is minimum. Okay. Now, whatever be the tour from wherever you are in our case, we are starting from one. Our tour consists of an edge. It will consist of an edge 1 comma k, 1 comma k, where k is some intermediate vertex. Let us take there are some n vertices. We are starting from vertex 1, and our tour will start from 1 and goes to an edge where it goes to a vertex k, so that the edge is 1 comma k. And what does this k belongs? This k uh, this k belongs to the set of vertices other than 1. So other than the vertex 1, we are going to a vertex k from 1, and the path from vertex 1 goes through each of the vertex other than this 1 and k only once. Only once. Again, I tell you, we are starting from vertex 1, and to start the tour from vertex 1, we go to a vertex k. K might be any of the remaining vertices of this graph. Okay. Then from K, we visit all the remaining vertices exactly once and come back to the vertex 1. That is what our plan is. Now, if we claim that this particular tour is minimum, then the path from vertex K to the vertex 1 should be minimum. Okay, for our convenience sake, let me take this particular graph. Okay, let me start from vertex 1. Then I can go to vertex 3, start from vertex 1 to 3. Then from 3, somehow I should visit all these vertices and come back, remaining vertices 2 and 4, and come back to the vertex 1. That is what my aim is. If such a tour is minimum, then that is the tour I am aiming for. So it is not necessary that from 1 I should go to 3, or I can go to from vertex 1 to 2, and from 2 I can go to either 4 and 3 and come back to vertex 1, or from vertex 1 I can go to vertex 4 and visit the remaining vertices 2 and 3 and come back to the vertex 1. Whatever be it, my aim is to have the tour of minimum length, minimum cost. So that is what my aim is. That's what my aim is. So when you are starting from vertex 1, you go to any of the remaining vertex k, and after visiting that vertex k, you are visiting the remaining vertices of the graph and come back to the vertex 1. So when you are visiting the remaining vertices, they should be visited only once. Only once. So otherwise you will not get a tour of minimum length. Okay. Okay, let me give one expression. Let g of I comma s, let g of I comma s be a tour of shortest path from vertex 1. Okay. Let g of I comma s be the shortest path. Shortest path with minimum length. Shortest path with minimum length. Okay. Then, what is my aim? That is, what does it mean? So this expression, I want you to keep it very carefully. You are starting from vertex 1, vertex I, visit all the vertices of S and come back to the vertex 1. That is what the meaning. Let G of I comma S be a path from with minimum length and visit all vertices of the set S and come back to vertex 1. That is what the meaning of this particular expression G of I comma S. If that is so, what I am trying to find? I try to find G of, I am starting from vertex 1. I am starting from vertex 1 and visit all the remaining vertices. So the set of vertices are V and the remaining vertices means V minus 1. V set of vertices minus my first vertex 1. So visit all these vertices and come back to this one. Come back to the vertex 1. This is what I am trying to find. I am starting from vertex 1, visit all the remaining vertices and come back to the vertex 1. That is what my aim is. If that is so, then what is this one? This G of V1 comma V minus 1 is nothing but minimum of cost involved from vertex cost involved from vertex 1 then to a vertex k could be any of the remaining vertex, one of the any of the remaining vertex plus then from the vertex k visit all the vertices and come back to the original vertex. So what is that one? That is nothing but G of, I'm starting from vertex k and visit all the remaining vertices, what are other than this k. So that is nothing but V minus 1 comma k. V minus 1 comma k. This is what I am trying to find. So it is a recurrence relation. Okay. So again, I want you to understand this particular thing very carefully. Then only we can proceed with some example problems. I'm starting from vertex 1. Visit all the vertices other than the vertex 1. That is what my aim. So when I try to do that, I start from vertex 1 to some vertex k. This vertex k could be any of the remaining vertices, any one of the remaining vertex. So C1k plus then from that vertex we have to visit the remaining vertices other than this 1 and k and come back to this vertex 1. Okay, if that is so, we will find this G of 1 comma V minus 1. So when I try to solve this one, I have to expand this one for all the remaining vertices, So when we go for some example problems, you will understand these concepts very easily. We go for some example problem. Example. For convenience sake, I have already solved one problem and I will take this one. Okay, this is the problem we are going to find. So what does it mean? What does it say? Starting from any of these vertex, visit the remaining vertices exactly once and come back to the original starting vertex. I could start from vertex 1, visit 2, 3, 4 and come back to vertex 1. Or I could start from vertex 3, visit the remaining vertices 4, 1, 2, and come back to vertex 3. Or I could start from vertex 2, visit the remaining vertices only once and come back to vertex 1. Okay, that is what my problem. Okay, so wherever I am starting, find the minimum cost tool. And this one is the cost matrix of this given graph. You know what is the cost matrix? That is nothing but a two-dimensional representation of the given graph. Two-dimensional representation of the given graph. Okay. For convenience sake, I have drawn the cost matrix in the matrix form. Let me remove these things. Okay. So what does this cost matrix says? The edge, the value of edge between 1 and 1 is 0, 1 and 2, 1 and 2. This is, see in this cost matrix, this is 1, 2, 3, 4 here. 1, 2, 3, 4. First, for your simple understanding, I have drawn it like this. Okay. The cost between 1 and 2, 1 and 2 is 10. 10. Cost between 1 and 3, 1 and 3 is 15. Okay, the vertex 1 and the vertex 3. So the red marked things are vertices, vertices. Okay, between 1 and 3 is 15. 1 and 4 is 20. 20, that is given here. Like this, 4 and 1. 4, 1. This is 8. So it is 8. 4 and 2, 8. 4 and vertex 4 and 3, 9. Vertex 4 and 20, 0. These things are given here. Okay. So using this cost matrix, we are going to solve this one. Okay. So from wherever the let me start from vertex 1. Vertex 1 for convenience state. Okay. So if I start from vertex 1, I could visit to remaining vertices and I should come back to the vertex 1. Okay. So whatever going to be the final vertex, I should come back to the vertex 1. So I need g of 2 comma 5, g of 3 comma 5, g of 4 comma 5. What is that 5? Empty set. Empty set. So I need that expression. So let me compute g of 2 1 comma 5. Okay, g of 1 comma 5 is empty set. Okay, equal to 0. Okay, starting at vertex 1, visit none of the vertex and come back to the vertex 1 is 0. The cost is 0. Similarly, g of 2 comma 5. What does it mean? Start from vertex 2. Start from vertex 2, visit none of the vertices and come back to the vertex 1. That is nothing but the edge between 2 and 1. Edge between 2 and 1. What is this 2, vertex 2 and 1? What is the value here? 5. So this is 2 comma 5 is 2 comma null is 5. This is 5. Similarly, g of 3 comma visit none of the vertices and come back to the original vertex. G of 3 comma 5. What is this? 3, come back to the vertex 1. So 3, 1. It is 6. It is 6. Similarly, g of 4, 4 comma 5 equal to fourth one path, that is 4 1, that is 8. That is 8. Okay. Now, I expand this one, this expression. What is this one? This is the expression. I have to expand this one. Formula, control V. So, this is nothing but g of start from vertex 1, visit all the remaining vertices. In this graph, what are the vertices given? 1, 2, 3, 4. So other than 1, what are the vertices? 2, 3, 4. So it is nothing but 2, 3, 4 equal to, what does it mean? Start from vertex 1, visit all these vertices and come back to the vertex 1. Okay, so from vertex 1, I may go to vertex 2 and visit the remaining vertices and come back to vertex 1, or from vertex 1, I may go to vertex 3 and visit the remaining vertices 4 and 2 and come back to the vertex 1, or from vertex 1, I may go to vertex 4 and visit the remaining vertices and come back to the vertex 1. So this expression should involve all these cases, and the minimum of those values that are found out is the final value. So this I can write it as minimum of from vertex 1 I can go to vertex 2. If that is so, what is the cost involved? C1 2 plus, then after visiting vertex 2, from there visit the remaining vertices. So g of 2 comma, what are the remaining vertices? 3 and 4. 3 comma 4. Okay, I find this expression, value of this expression, comma. Then from vertex 1 I can go to vertex 3. So C1 3. Then from vertex 3 I go to G of the remaining vertices. What are these? The remaining vertices. G of 3 comma. What are the remaining vertices? 2 and 4. 2 comma 4. Okay. Or from vertex 1 I can go to vertex 4, then from vertex 4 I have to go to the remaining vertices, that is g of 4 comma remaining, what are the remaining vertices? 2 and 3. So 4 comma 2 comma 3. 2 comma 3. Okay. So I have to compute what is this value. I have to compute what is this value. I have to compute what is this value and put them here, get the minimum of this one to get the minimum of this expression, and that is the final expression. So to do this, I should get what is this value is, what is this value is. So I put it here. So what does it mean? Start from vertex 2, visit these vertices and come back to the vertex 1. So when I start from here, either I can go to the vertex 3, then from 3 I go to vertex 4 and 1, or from vertex 2 I can go to vertex 4 first, then visit 3 and come back to the vertex 1. So these are the two cases. So I should take into consideration both the cases. So minimum of from vertex 2 I go to the 3. So C to 3 plus G of so from 3 so I'm going to the vertex 3. From 3 I should go to the vertex, remaining vertex, what is it? 4, and come back to the vertex 1. Come back to the vertex 1. Or what is the other chance? From vertex 2 I can go to the vertex 4. Okay, then G of from vertex 4 I can go to the vertex 3. I can go to the vertex 3. So this is the thing. Okay. So to get this expression, I should solve what is this g of 3 comma 4 comma g of 3 comma the set 4. Okay, I should solve this one and get this one. What is g of 3? What is this g of 3 comma 4? What is g of 3 comma? What does it mean? This says that g of 3 set 4 is nothing but, what does it mean? Start from vertex 3. Start from vertex 3 and go to the vertex 4, then 4 to 1. So what is that path? 3 to 4, 4 to 1. So what is this 3 to 4? 3 to 4. 3 to 4 is 12. So this is nothing but 3 comma 4 plus 4 comma 1. This is what the meaning. So what is this 3 comma 4? 3 comma 4 is 12 plus 4 1. 4 1 is 8 equal to 20. So this 20. So I have found this 3 comma 4 as 20. So I already, what is the C12? The value from vertex 1 to 2, 2. Value from vertex 1 to 2 is 10. Value from 1 to 2 is 10. So I supply this value here. Similar, before that, I compute these things also. These things also. What is the G of 3 comma 4, G of 4 comma 3, G of 4 comma 3. What does it mean? The value of 4 comma 3 plus 3 comma 1, 3 comma 1, that is equal to 4 3. What is this 4 3? 4 3, it is 9. It is 9. So this 9 plus 3 1. 3 1, it is 6. 6, that is equal to 9 plus 6 is equal to 15. So I have found out these expressions. So let me supply these things here. Okay. So this is nothing but this is equal to minimum of a minimum of what is C2 3? The edge between 2 and 3. 2 and 3, it is 9. So 9 plus 9 plus G of 3, 4, we have computed it as 20. So it is 20, comma, then C2, 4, 2, 4, it is 10. 10 plus G of 4, 3. G of 4, 3, we have computed it as 15. So you put that here. Okay, that is equal to 9 plus 20 is equal to 29. 10 plus 15 is equal to 25, which is minimum. 25 is minimum, and this one is 25. So this we have computed one. This value, one of the values. So G34 is computed to be 25. That I want you to know. Next, similarly, we are going to compute what is this one? G of 3 to 4. G of 3 to 4. So, just like the previous case, G of 3 to 4 is a minimum of, what does it mean? From vertex 3, visit one of these vertex, visit these vertices and come back to the vertex 1. So, from vertex 3, I can go to C32 plus G of from vertex 2, G of 2 comma, what is the remaining vertex? 4 comma, then from 3 I can go to the 4 also. From C 3 4 plus G of, from 4 I can go, I should go to the 4 comma vertex 2. Vertex 2. Okay. This is the thing. So I should get what is this G of 2 comma 4 and this one. So what is this G of 2 comma 4? This is nothing but 2 to 4 and 4 to 1 path. 2 to 4 and 4 to 1 path. So 2 to 4, this is equal to, now C3 2. So 3 and 2, 3, 2, it is 13. So minimum of C3 2 is 13. Plus, what is this G2 4? 2 to 4, then 4 to 1. 2 to 4. 2 to 4 is 10 plus 4 to 1. 4 to 1 is 8. 8, comma. Then, what is the next one? 3 to 4. See, 3, 4. 3, 4, 12. This is 12. 12 plus, what is this? G4 to 4 to 2, 2 to 1. 4 to 2 is 8. This is 8 plus 2 to 1. Yes, 2 to 1. It is 5. This is 5. Okay. That is equal to, you complete these values. 10 plus 13, 23 plus 8, 31. Here it is 12 plus 8, 20 plus 5, 25. So which is minimum? 25 is minimum. So this is minimum. So this is also we have computed. That is G. This is also we have computed. Next, we have to compute what is the remaining thing. We have to compute G4. This one we have to compute. This one I have to compute. Okay, so this is nothing but minimum of from vertex 4 I can go to vertex 2 or vertex 3. So I should consider both the cases. Suppose I go for from vertex 4 I go to the vertex 2. Then from vertex 2 I have to visit from vertex 2 I have to visit the remaining vertex 3. Remaining vertex 3 comma or from vertex 4 I can go to the vertex 3. So C 4 3 C4 3 plus G of from vertex 3 I should go to the vertex 2 3 comma vertex 2, that is equal to the minimum of now C4 2 4 2 the edge between 4 and 2 4 and 2 it is 8 it is 8 8 plus what is this G23 from vertex 2 go to the vertex 3 then from 3 vertex go to the 1. So see 2 3 and 3 1 path 2 3 2 3 it is 9 plus 3 1 3 1 it is 6 comma similarly 4 3 4 3 it is 9 9 plus what is this G of 3 comma 2 from vertex 3 go to the vertex 2 from vertex 2 go to the vertex 1. So 3 3 2 and 2 1 path 3 2 it is 13 plus 2 1 path 2 1 path it is 5. That is equal to now you compare this thing 9 plus 8 17 17 plus 6 23. Here it is 9 plus 13 22 plus 5 27. So 23 is minimum. 23 is minimum. So I have computed this one also. Okay. Now this is available, this is available, this is available. Now I can go for this these things. Okay. Let me copy it now here. Minimum of what is this C1 2? The edge between vertex 1 and 2. Vertex 1 and 2. It is 10. This is nothing but 10 plus G234. G234 I have computed as 25. So this is 25. Then C13, the edge between 1 and 3. 1 and 3. It is 15. 15. G of 324. G of 324 I have computed as 25. So this is nothing but 25. 25. C14, vertex 1 and 4. It is 20. 20 plus G423. It is 23. 23. You solve these things equal to minimum of 10 plus 25, 35. 35, comma, uh, 15 plus 25, 40. 40, comma, 20 plus 23, 43. 43. Which is the minimum? 25 is minimum. Sorry, this 25 plus 35. Sorry. 35. Which is minimum? 35 is minimum. So the minimum cost tour is 35. So this is the final answer. This is how we find the minimum cost tour. So when you started from vertex 1 and visit all these vertices and come back to the vertex 1, the minimum cost involved will be 35. So here we are optimizing the cost of the tour. Okay, so optimal tour that is taken into account, that is found out. That is why it is a dynamic programming problem. So whatever be the initial state, from the remaining state we are trying to optimize it. Okay, so this example explained to you how your dynamic programming is employed. See, it is a simple problem. It is a very practical problem. Traveling salesman problem is a very practical problem. It is in a real life situation. It is very much employed usually here. So this explains this dynamic programming problem set strategy. In the coming classes, we will go for yet another problem solving strategy called backtracking. That is also involved here. That is also a very good problem solving strategy that we will discuss in the next class. See you in the next class on backtracking problem solving strategy. See you tomorrow.